We continue our lecture 5 on sequences and summations. Example 11, compound interest. Suppose that a person deposits $10,000 in his savings account at a bank yielding an impossibly rich 11% per year with interest compounding annually. How much will be in the account after 30 years? Solution. To solve this problem, let P subscript n denote the amount in the account after n years. Because the amount in the account after n years equals the amount in the account after n minus y years plus interest for the nth year, we see that the sequence P subscript n satisfies the recurrence relation P sub n is equal to P sub n minus 1 plus 0.11 times P sub n minus 1 is equal to 1.11 times P subscript n minus 1. The initial condition is P sub 0 is equal to $10,000. We can use the iterative approach to find the formula for P sub n. Note that P sub n is equal to 1.11 times P sub n minus 1, which is equal to 1.11 to the power n times P sub 0. When we insert the initial condition P sub 0 equal 10,000 into the formula P sub n equal 1.11 to the n power, P sub 0 is obtained. Inserting n equal 30 into the formula, P sub n is equal to 1.11 to the n power 10,000 shows us that after 30 years the account contains $228,922.97. Special integer sequences. Questions for identifying the algebraic representation for a sequence of numeric terms. Are there runs of the same value? That is, does the same value occur many times in a row? Are there terms obtained from previous terms by adding the same amount or an amount that depends on the position of the sequence? Are terms obtained from previous terms by multiplying them in a particular amount? Are terms obtained by combining previous terms in a certain way? Are there cycles among terms? Example 12.1. Find a formula for the sequence whose first 5 terms are 1, 1/2, 1/4, 1/8, and 1/16. Solution. We recognize an exponential sequence where powers of 2 appear in the denominators, 2, 4, 8, and 16. Hence, the sequence is a geometric progression with a equal 1 and r equal 1/2. Recall that a geometric progression has the form AR squared, and so on to AR to the nth power. In this case, A sub 0 equal AR to the 0 power is 1 times 1/2 to the 0 power equal 1. You can see that A subscript 2 is AR squared, 1 times 1/2 to the 2 power is equal 1/4, and we can see the other terms are produced in exactly the same way. Example 12.2. Find the formula for the sequence whose first 5 terms are 1, 3, 5, 7, and 9. We recognize the common difference between terms. The difference is 2, recalling that the form of an arithmetic progression is A plus D, A plus 2D, and so on to A plus ND. We see that A is 1 and D is 2. A sub 0 is equal to 1, A sub 1 is equal to 1 plus 2 is 3, A sub 2 is equal to 1 plus 2 times 2 is equal to 5, and so on. Example 12.3. Find a formula for the sequence whose first 5 terms are 1, minus 1, 1, minus 1, 1. We recognize an exponential sequence where powers of minus 1 are terms of the sequence. Odd powers of minus 1 produce minus 1, and even powers of minus 1 produce 1. Hence, the sequence is a geometric progression with A equal 1 and R equal minus 1. A sub 0 is AR to the 0, which is minus 1 to the 0 power, which is 1. AR subscript A to the 1 power is AR to the 1 power, which is 1 times minus 1 to the 1 power, which is minus 1. And we can see that we generate 1 and minus 1 alternatively. Example 13. How can we produce terms of the sequence if the first 10 terms are 1, double 2, triple 3, quadruple 4? Solution. In this sequence, the integer 1 appears once, the integer 2 appears twice, the integer 3 appears 3 times, and the integer 4 appears 4 times. A reasonable rule for generating the sequence is that the integer n appears exactly n times, so the next 5 terms of the sequence would be all 5s, following 6 terms would be all 6, and so on. The sequence generated this way is a possible match. Example 14. How can we produce the terms of the sequence if the first 10 terms are 5, 11, 17, 23, 29, 35, 41, 47, 53, and 59? Solution. We need to speculate. Is this an arithmetic progression? Is this a geometric progression? Is this a combination of an arithmetic and geometric progression? Let us guess the progression is arithmetic and employ the table below to discover the pattern of the sequence. Here is our subscript I, here is the I plus 1 term, and here's the ith term. So we subtract from the ith plus 1 term the ith term, and we see that the constant is 6. We see that this is an arithmetic progression where d is equal to 6, and a is equal to 5, and a sub n is equal to 5 plus 6n for n equals 0, 1, 2. How can we produce the terms of the sequence if the first 10 terms are 1, 3, 4, 7, 11, 18, 29, 47, 76, and 123? Solution. Observe that each successive term of the sequence, starting with the third term, is the sum of the previous 2 terms. That is, 4 is equal to 3 plus 1, 7 is equal to 4 plus 3, 11 is 7 plus 4, and so on. Consequently, if L sub n is the nth term, in the sequence, we guess that the sequence is determined by the recurrence relation L subscript n is equal to L subscript n minus 1 plus L subscript n minus 2 with the initial conditions L subscript 1 and L subscript 2 equal 3. The same recurrence relation as in the Fibonacci sequence, but with different initial conditions. This sequence is known as the Lucas sequence after the French mathematician François-Edouard Lucas. Lucas studied the sequence and the Fibonacci sequence in the 19th century. Example 16. Find a formula for the sequence whose first few terms are 1, 7, 25, 79, 241, 727, 21, 85, 65, 59, 19, 681, and 59047. As before, find the difference between successive terms. So we find the difference is 6, 18, 54, 162, and so we find common factors and the remaining factor. The common factor for each one is 2. 2 times 3 is 6, 2 times 9 is 18, and so on. And the remaining factor is 3, 9, 27, 81, which we recognize as powers of 3. So we propose a geometric progression. A sub n is equal to 3 to the n minus 2 for n equal 1, 2, and 3. And we arrive at the sequence. Definition 3.1. Summation notation is used to express the sum of a sequence, and any one of the following forms may be used. We have my favorite form, where we have the capital Greek letter sigma, and on the bottom we have the index variable j, and we have its initial value. On the bottom and on the top we have its final value, and we go from the initial value to the final value inclusive. And then we have the term, which is going to be some function of j to give us a sub m for the values a m through n, as we see here. Another way we can do this is we can put the initial and starting values in front of in the front, top and bottom of the capital sigma, or we can put them on the bottom and give the index range as we see here, m less than or equal to j less than or equal to n. Here the index of the summation runs through all integers, starting with its lower limit n and ending with its upper limit n. A large uppercase Greek letter sigma is used to denote the summation. use the summation notation to express the sum of the first 100 terms of the sequence A subscript j, where j is equal to 1 over j for j equal 1, 2, 3. I prefer it this way, j equal 1 to 100, 1 over j. What is the value of j equals of the sum of j from j equal 1 to 5 of j squared? We have the sum from j equal 1 to 5 of j squared is 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared is equal to 55. Or, from the formula, the sum of k equal 1 to n of k squared is n times the quantity n plus 1 times the quantity n plus 2n plus 1 all over 6. And we arrive at the same value. Example 19. What is the value of the sum from k equal 4 to 8 of minus 1 to the k power? The sum from k equal 4 to 8 is 1 plus minus 1 plus 1 plus minus 1 plus 1 is equal to 1. Example 20. Suppose we have the sum from j equal 1 to j equal 1 to 5 of j squared, but want the index of the summation to run between 0 and 4 rather than from 1 to 5. To do this, we let k equal j minus 1. The new summation index runs from 0 because k equal 1 minus 1 is equal to 0 at the lower bound when j equal 1, to 4 because k equal 5 minus 1 equal 4 when j is equal to 5. And the term j squared becomes k plus 1 squared. Is easily checked that both sums are equal to 55. Theorem 1. If a and r are real numbers, and r not equal to 0, then the sum from j equals 0 to n of ar to the power j is, if r not equal to 1, ar to the n plus 1 minus a over r minus 1, or if r is equal to 1, n plus 1 times a. Example 21. Evaluate the double sum I equal 1 to 4, j equal 1 to 3 of the product ij. Solution. First, evaluate the inner sum and find a function of f of I where I is the index of the outer sum. In other words, eliminate both the inner summation and the inner index variable. So we find the double sum of the product is equal to the sum from I equal 1 to 4, as before, of I plus 2I plus 3I, or 1I, 2I plus 3I, which is 6I from deal. And then we can next evaluate the outer sum, and we arrive at I is equal to 1 to 4. We can bring the 6 out front, and we can have the sum from I equal to 1 to 4, and we can use our formula to find the sum of an arithmetic sequence, n times n plus 1 over 2, where n is 4. 4 times 5 is 20 over 2, which is 10 times 6 is 60. Here are some useful summation formula, which I leave you to peruse. You can also find them in our text. Example 23. Evaluate the sum from k equal 50 to 100 of k squared. The mechanism to do this is to find the sum from k equal 1 to 100 minus the sum from k equal 1 to 49, and then we will have it. So we find that it's 297,925.